Support for Curious Crew is provided by MSU Federal Credit Union, offering a variety of accounts for children and teens of all ages while teaching lifelong saving habits. More information is available at msufcu.org. Also by the Consumers Energy Foundation, dedicated to ensuring Michigan residents have access to world-class educational resources by investing in nonprofits committed to education and career readiness. More information is available at consumersenergy.com/foundation. And by viewers like you. Thank you.
Hi, I'm Rob Stephenson, and this is
Curious Crew!
Welcome to the show, everybody. We always like to start every episode with a couple of discrepant events because discrepant events stimulate
curiosity!
That's exactly right, and I've got some fun plans for you today. And in fact, we're going to start with something called the Cruising Crew Trials. And this is going to involve this long, stretchy band, a skateboard, and a special app on my phone that is an accelerometer. Now, one of you is going to get moving, and I think we're going to start with Lake. Let's get set up. Okay, so we've got Lake set up here, and Abigail, Emmanuel, thank you so much. They're going to be supplying some tension on this band, trying to hold that really steady. Now, Nicholas and Lynn, can you do me a favor? In just a moment, I'm going to have you pull Lake back all the way to this blue mark on the floor, and on the count of 3, we're going to let her go, and Lake, you're going to start that app. You ready? Let's pull her back. Okay, pulling her all the way back to the blue mark. Abigail, Emmanuel, hold it tight. Let's count it down, everybody. 3, 2, 1, go! Nice job, there she goes. Goodbye, Lake, excellent job. You can hit pause on the accelerometer. I'm gonna be really interested to see what that looks like. You know what? I think it's time to launch someone else. Leon, we're gonna get him ready. Okay, Leon's ready for the second trial. Let's pull him back all the way to the blue mark again and help me count down. 3, 2, 1, go. There he goes. Goodbye, Leon. Go ahead and hit pause on that accelerometer. Great job, Leon. I think I'm ready for one more, and it's gonna be Ian. We're gonna get him ready next. Okay, Ian's ready, so let's pull him back to the blue mark, and we're gonna count it down. 3, 2, 1, go! There he goes! Goodbye, Ian! And you can hit the pause. Now, surprisingly, I'm gonna do Ian one more time. What? You'll see why. So the last trial, Ian's ready, but this time, when you pull him back, only pull him to the green mark. Let's try it. Right there, and 3, 2, 1, go! Oh, that was so disappointing. Now that's where it gets interesting. We're gonna have to talk about this. Let's clean this up and do a little debrief. So some of you look pretty good cruising on that skateboard, and we made some interesting observations, right? I'm gonna ask 3 of you to really think about those observations, to see if you can come up with some scientific modeling and explain them by the end of the show. You can use your background knowledge, evidence that you learn. Who would like to do a little modeling moment today? Okay, Emmanuel, Julia, Abigail, you 3. Now, does anybody have a guess what we're gonna be investigating today? You really have a guess. What is your guess, Lake?
Momentum.
Momentum, I love that with such confidence. That is actually a part of what we're gonna be investigating. We are gonna explore Newton's second law of motion. Stick around, it's gonna be full speed ahead.
Let's see if we can figure this out.
I've never seen an accelerometer before. It was cool how it detected the movement of the cart.
I know, we could definitely tell that Lake accelerated faster than Leon, and Iad's first ride, there was more acceleration.
The input force definitely makes a difference in an object's acceleration.
Sir Isaac Newton was an English physicist and mathematician who explained the relationship between forces on an object and the object's motion. In 1687, he published his laws of motion in the Principia Mathematica. His second law of motion describes how the acceleration of an object depends on both force and mass. When you ride your bike, you can accelerate by pushing on the pedals, and if you apply more force on the pedals, you can go even faster. See you later. Well, you both did a really good job riding those skateboards. Maybe next time, okay, Nicholas? Sorry about that. But we do need to try to make sense of Newton's second law of motion. And I want to start with these two spheres right here. What do you notice about these two? Like,
One thing is they're not even moving.
okay, so we're talking about motion and they're not in motion. That is a super great observation. And in fact, they are experiencing forces though. There's a force of gravity, and there's actually a force called the normal force, which is pushing up. And if they're balanced, things stay still. But what could we do, Lake, to try to get this first rubber ball to move?
Well, we can maybe touch it or move it a little.
Okay, touch it, move it a little, push it a little. Okay, I've got a really crazy idea. We're gonna try something. This will be fun. I have a little foam dart that I'm going to launch at this ball to see if we can get it to move. Now, I also want to try something though. Right before we launch it, Lake, I'm going to ask you to put your hand behind it, right up against the ball, because I'm going to ask you a question about that. But safety first, everybody. Let's get some goggles on here. We don't want any stray pieces of foam headed our way. Okay, so we've got this ready. Lake, go ahead and put your hand behind it, and we're going to launch it. Let's see what happens. Oh my gosh! Oh my gosh! Oh my! It went flying over there. Okay, so could you feel the force?
I can feel a little.
You could feel that, couldn't you?
Yeah.
Okay, so we're gonna try it one more time. This time, I'm not gonna have you stop it. You ready? Oh! So it sort of moved over and hit the other ball, didn't it?
Oh yeah, the other ball stopped it.
Oh, interesting. Okay, now that other ball is kind of an interesting one. That is a bowling ball. A 16-pound bowling ball. Ian, do you think we're gonna be able to move it with this little dart? What do you think?
Absolutely not.
He says with confidence, absolutely not. I think you are right. Okay, take that off. How come we couldn't move that, Ian?
Because it's 16 pounds and the other one's really light.
The other one's really light. And so obviously there's a lot of mass. Both of those are experiencing gravity, right? Both of them are experiencing a normal force, and right now they're still. I want to look at something else that's still. Take a look at this block. It's still. Gravity, normal force, they're balanced. Let's see if we can make it unbalanced. The coolest thing about acceleration, that means when something moves, changes direction or speed because of a force, we're gonna see if we can make that accelerate. But let's see if we can try it with these three spheres. What are you noticing about those, Nicholas?
I noticed one is foam,
Yep.
one is rubber, and one is steel.
Okay, excellent. Let's start with the foam one. Now keep in mind, the block right now, it's balanced. It's not moving. We've got force of gravity, normal force going up. Now if we add all of those forces together, that's called the net force. Let's see if we can add another force here. Changing the net force. Did it make a difference? No. Okay, how about the rubber ball? Will this net force make it unbalanced? Let's see.
A little, I think.
A little bit.
7 centimeters.
Oh, very good. Okay, so let's see what we get with the steel one. Oh, that was
60 centimeters.
That's really good, really good. A lot of mass, a lot of acceleration. We got some unbalanced forces, and that moved. Acceleration in Newton's second law of motion describes an object's change in speed or direction over time. Now, objects can experience many kinds of forces, including pushing, pulling, twisting, or squeezing. And those forces can be either balanced or unbalanced. Imagine a game of tug of war. If there are similar forces on both sides, the system is balanced and the rope doesn't move even though a lot of force is applied. But if we add more mass and pulling force to one side of the rope, it gets unbalanced and the rope begins to accelerate. Wow, what a contest! So we know that unbalanced forces can get an object to accelerate. But what are those forces? What kind of forces can you think of, Abigail?
Pushes and pulls.
Pushes and pulls. Those are great examples of forces, right? So take a look at these cars right here. Tell me what you notice about these, Abigail.
Well, I noticed that there's like a little spring here, and then there's not one on the other.
Okay, so there's a spring here, and actually let's take a look at that. And so if I push it down, it'll pop back up. You might recognize this. This actually goes to a top of a bifold door to help keep the door in its track. Now, if we push this together and I do like this and then let go, what do you think's gonna happen? What do you think, Emmanuel, what do you think's gonna happen?
I think they're gonna separate.
Okay, you think they're gonna separate. Let's try this. We're gonna put it right about in the middle of the meter stick, and I squeeze it together, and they separate. Let's do it again. Ooh, that was a good one. What are you noticing about how they traveled here, Anderson?
They both move away from the point where they started at about the same distance.
Oh, excellent. Okay, and they really did. It's a really close travel distance, which makes sense because we're talking about something with similar mass.
Yeah.
So let's try something else. Let's change the mass in the system. In fact, I have these extra blocks, and we're gonna put them on top of this car. And you can see I've got a little dowel, and I'm just gonna stretch this over, and now we've increased the mass. Okay, what do you think is gonna happen now? Anderson, what do you think is gonna happen now?
I think only the block with the spring is gonna move because this one's gonna be too heavy. It'll take a lot more energy to move.
Okay, let's check it out. Oh my gosh, was that a good prediction? That kind of makes sense, doesn't it? So we have a lot of mass here, and so this one had a lot of acceleration. So interesting to think about. If they're experiencing the same force, they both have exactly the same pushing force, but this one's gonna travel more. Now, I wanna try this another way. Ava Gale, you mentioned pushes and pulls. Let's try this with a pull scenario. So I've got 2 blocks, and I've drilled a hole where I could recess a couple of eyelets down inside there, and we've got them attached with a rubber band. So if we stretch them apart and then let them go, Emmanuel, what's gonna happen?
They're gonna snap back.
And they're both experiencing the same force, right? Because it's the same rubber band. We've got elastic potential energy. I'm gonna pull them back a pretty similar distance, and let's see what happens. Oh, nice. Did you notice where they made contact?
Right in the middle.
Right in the middle. Same force. Okay, let's change things up. We're gonna put a couple of extra blocks on this side and do it again. We're gonna stretch them apart and see which one accelerates more. You guys have a prediction?
This one.
You agree? Okay, let's take a look. Oh yes,
Yeah,
that is
wow.
exactly true. We'll do it one more time. So they have the same force, but this one accelerates a lot more. Here's the rule as far as Newton's second law. If 2 objects experience the same force, the one with less mass is gonna accelerate more. Each time you go shopping, you get first-hand experience with Newton's second law of motion. Imagine you walk in the grocery store and begin to push the empty shopping cart. It's easy to get the cart accelerating, but each time you add more in the cart, you increase the cart's total mass. Pushing a very full cart is a lot more difficult. If you push the full cart with the same force as before, you may have noticed that it takes longer to get it moving and harder to stop it. Oops. So have you been having fun investigating Newton's second law of motion today? Yeah! I'm so glad. Now I've got a great STEM challenge for you. You're going to be making a catapult, but this is not an ordinary catapult. Yes, it's going to apply a force to a mass and make it accelerate, but that mass is going to be a marshmallow. And so I like to call these catapults confectionery catapults. Now there's something else I want you to try. Each table is going to make 2 prototypes. You have to decide how big your fulcrum is going to be. You ready to get started? Yeah! All right, go for it. Have fun.
Which one you want to start with?
The bigger one.
I'll tie this one together.
So we was creating a launcher to measure how far the marshmallows went.
This one has 7.
For the STEM challenge, we received popsicle sticks, rubber bands, and a spoon.
All right, I got this. All right, And the first thing we did was make the fulcrum. Oh yeah. A fulcrum is the point where like an angle is like changing from.
Okay, I'm gonna work on the other one.
I'm thinking in my head that we were gonna try a bunch of popsicle sticks and then not so many to see the difference between the 2.
As we were building, we realized that there was a lot more tension on the one with 7 popsicle sticks than the one with 2 in the fulcrum, and the goal was to launch them farther, so we tried to get the angle as steep as possible. Now, who's gonna make it into an X?
This is not right.
An issue you're running into is forgetting how to put the rubber bands onto the popsicle sticks to secure them.
You gotta put it in both.
I'm trying to push them both.
We had a good strategy, but I was kind of iffy at launching it because it kept going sideways. I don't know why. It didn't ever go straight, just went sideways.
I think the big marshmallow won't go that far because it's bigger.
Let me see yours. Oh,
There we go.
oh, that worked a little better.
Yes!
Oh boy, these are looking pretty good. I think we're just about ready to test them. Before we test these, I do want to get a sense of how many popsicle sticks you each used in your prototypes. Ian, let's start with you. What did you guys do?
We did 4 and 7.
4 and 7. Excellent. Okay, this table, Abigail, how about this one?
We did 5 and 7.
5 and 7, okay. And Julia?
We did 7 and 2.
7 and 2. So 7 is really, really popular. I probably would have done that too. Now, we're gonna need to move the tables out of the way so we can line these up, and then we're gonna have some fun launching some marshmallows. Okay, so now we're ready to test these catapults, and we've got them arranged by the size of your fulcrums. So we have a 7, 7, 7, 5, 4, 2. And you'll notice when we look at the 2, that's angled way further back than the 7. So that's gonna be kind of interesting when we try to do a launch. We're starting with the jumbos. What was the mass of the jumbo marshmallow, Ian?
The mass of the jumbo marshmallow is 28.5 grams.
28.5 grams. On your mark, 3, 2, 1, launch. Oh, you actually got some distance. Okay, it's time for the middle size. Grab your middle size. What's the mass on the middle size, Abigail?
The mass was 8.2 grams.
8.2 grams. Let's see, do you think this is gonna accelerate more or less? Not only are we gonna look for distance, look for height. You ready? Let's count it down. 3, 2, 1, launch it! Oh, okay, that was interesting. Okay, one more to test. Get out the mini. Julia, what's the mass on the mini marshmallow?
The mini marshmallow is 0.6 grams.
0.6! Oh my gosh, 0.6. You ready? Let's count it down. 3, 2, 1, launch! Whoa! So which one really got the best acceleration, you guys? The minis, of course. Confectionery catapults are a great way to investigate Newton's second law of motion. And the projectiles? They're pretty sweet too. The crew saw how the marshmallows with less mass traveled higher and further. But what if we changed the amount of force in the catapult? Would the larger marshmallow travel further than it did before? Think about it this way. When you kick a soccer ball, it accelerates. But the larger the ball, the harder you have to kick it. So applying more force in the catapult would also increase acceleration on a larger marshmallow. Or you could always try kicking the marshmallow. So we've figured out that unbalanced forces are an essential part of Newton's second law. This time though, Leon, you're going to be the force, okay? And in fact, I hope you're not feeling unbalanced or unsteady. No, just for this challenge, you notice we have a skateboard here. What I'm gonna ask you to do is you are going to push each of the girls in sequence. I'm gonna have you push Julia first, just one single push, and then she's gonna get off, and then we're gonna do the same thing with Ann Lynn, and then you're gonna tell us what you notice, okay? All right, let's get this one set up. Okay, so we got Julia set, one good push. You ready, Leon? Okay. Look at that straight back. Ooh, she's accelerating nicely. Well done, well done. The force. All right, Ann Lynn's next. Okay, Leon, now we're gonna do Ann Lynn and notice the difference. Go for it. There she goes. Well done, Ann Lynn. All right, nice job. I think we need to debrief this. All right, so that was great, but Leon, what did you notice as far as the difference between these two?
Well, when I pushed Julia, since she's shorter, it didn't take as much force, she had greater acceleration and she went further. But when I pushed Ann Lynn, since she's older and taller, it took more force to push her forwards with more acceleration and distance.
That's excellent. I couldn't have said it better myself. Now you're probably wondering, we have something else to do, and it's gonna relate to my tie. Check it out. Have you guys ever gone bowling?
Yeah.
Okay, so we go bowling. That's a great way to investigate Newton's second law. We are going to apply a force with a bowling ball, and we are gonna roll that down and slam that into the mass, the pins, to try to get them all to accelerate. Okay, I've got some bowling balls here. Ann Lynn, when you go bowling, what size ball do you like to use?
About 8 pounds.
8 pounds. I have an 8-pound ball right there. That 8-pound ball is suspended up to the ceiling, so it's actually hanging. I'm gonna pull it back about 1 meter and let it collide into our mass, the box. Ann-Lynn, how far do you think that box is gonna accelerate?
A foot.
Maybe a foot. Let's give this a whirl here. Bring it back, try to be consistent with our input force. That was a pretty good prediction. Okay, now you might be wondering, all right, Dr. Reb's got another one over here. This one is 16 pounds. 16 pounds. So Leon, what do you think is gonna happen this time?
I think it's gonna be a little bit heavier to lift up the ball and drop it, but I think the box is gonna go a little further than I did last time.
Okay, so we're looking for a greater distance traveled. It is harder to pull back, you're right about that. Okay, and here we go. Okay, so we got a little more distance on that. Now that actually does make sense, and I could actually feel that weight as I pulled that thing back. Keep in mind, Newton's second law of motion says if we can apply a greater force, we can get greater acceleration. We know that the mass of an object will determine how much force will be required to change its speed or direction. Imagine throwing a softball and then a cannonball. That cannonball will require a lot more force because it has so much more mass. A rocket docking in space is another interesting example. If the pilot needs to slow down, go faster, or change direction, force from the engine will be required. Great docking maneuver! Sir Isaac Newton would be so proud.
Are you curious about careers in science?
Hi, I'm Olivia, and today I'm here with Rana Mohtadi. Rana, can you tell us where we are and what you do?
I'm a senior principal scientist at Toyota. I work on developing materials for batteries that can be hopefully implemented in our vehicles in the future.
How is STEM involved in your work?
Well, STEM is a core component in my work. We have physics, we have math, we have chemistry, so we need all of these tools to do our materials research.
So how do batteries actually work?
They allow us to store energy in the form of electricity. Here we have what we call a pouch cell type of battery. Everything is lying flat here. One side is the negative and another side is the positive electrode. And you have many of them. You can even run a car.
Wow. I feel powered up from learning about batteries with Rana Mohtadi. Explore your possibilities.
And now, back to Curious Crew.
So, we know that an object's acceleration depends on the net forces and the object's mass.
Right, but when Lake and Leon both rode the cart, the band pushed with a similar force, but their masses were different.
Yeah, since Lake has less mass, she traveled further and faster.
And in Iad's case, the mass was the same, but the force was different. And in his first ride, there was more acceleration.
So have you had fun investigating Newton's second law of motion today?
Yeah!
Oh my gosh, you said that with such force. Okay, it's now time to go back to look at our discrepant events at the beginning. And you might remember with this long bungee cord that we were using, right? Our cruising trials. Now, here's something I want you to think about. We were using a special app called an accelerometer. And I was having each of you pay attention to that. We've got some data here. In fact, Lake, we saw you hit a spike launch in that acceleration of 3 meters per second squared. Leon came in at 1.9, think about that. Iad's first attempt also at 3.0, but his second attempt was only 0.5. That's interesting. Now I know several of you have been thinking about this, and you have some explanation for this phenomenon. I'm gonna start with Julia. Bring us up to speed, Julia. What have you figured out between the comparison, especially between Lake and Leon?
We know that when they were pulled back into the band, there was elastic potential energy that would push them forward when released.
Right, because they both had the same pushing force.
And because Lake had less mass than Leon, she accelerated faster.
Okay, so we're pulling them back a similar distance. Okay, that makes sense to me. So what if we wanted Leon to accelerate as fast as Lake? Emmanuel, what could we do?
We could add more pushing force.
Oh, increasing the pushing force, that makes a lot of sense. And we already know that Leon's a force to be reckoned with, right? Okay, so now I want to think about Iad, because we did his twice. What did we figure out there, Abigail?
Well, because Iad went twice, the only thing that changed was the pushing force. And we could tell the bigger the push, the greater the acceleration.
And that is Newton's second law of motion, right? So the next time you're pushing a friend on a swing or pulling them in a wagon, or you're going bowling, or you might be pushing that shopping cart in the grocery store as it gets heavier and heavier, you can give a shout out to Sir Isaac Newton for his second law of motion. Now it looks like we got to get going too. So remember, my friends, stay curious and keep experimenting. Get your curiosity guide and see more programs at WKAR.org.
Support for Curious Crew is provided by MSU Federal Credit Union, offering a variety of accounts for children and teens of all ages while teaching lifelong saving habits. More information is available at msufcu.org. Also by the Consumers Energy Foundation, dedicated to ensuring Michigan residents have access to world-class educational resources by investing in nonprofits committed to education and career readiness. More information is available at consumersenergy.com/foundation. And by viewers like you. Thank you.
I know! Season 11, let's roll. Let's roll. Okay, here she comes. Say hi, Elena.
Hi, Elena. Hello.
See, you are all, no, let me try that again. La, 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 la. Okay, and to take two. Well, I was like, moon. And last but not least, that'll make it to the end of the show, I think. Right there.